Okay, so as I described in the last, just now, for those in class, that was 5 seconds ago. For people online, that was the last video. This type of searching gives you a path, not necessarily the shortest, because this one requires you to go from 0, 1, 3, 4, 6, 11, 9. But in reality, we could have gone 1, 4, 6, 11, 9, and thereby skipping 3 altogether. Because there is a link between 1 and 4, or there's not a link. Oh, there's a link between 1 and 6. So we could have just gone from 1 to 6 and completely skipped 3 and 4. Totally skipped 3 and 4. Okay. Totally.
Like tons, but no.
Totally. All right. What could we do instead? This was called a depth first search. What else could we do? Breadth first search. Awesome. How does a breadth first search work?
Jesus gives the bread first to his disciples, then to everybody else.
Isn't that
So they get the
distribution
bread
and not
first.
and not but that's distribution. Oh, I see. Bread first. Okay. All right. I got it. Any other ones? I like that one. I'll try not to make too many references in the code. No? All right. So the breadth first search. Well, so how hard was this code right here? Very hard? You really think so? Okay.
That means that the bread is harder.
All right. We'll do breadth first search. Int start, int end. All right. So when doing a breadth first search, what do we need to set up?
Jesus.
Whew. No. Well, sure. We could ask Jesus for help here.
You can ask him nicely. Maybe the compiler will help and actually have him say yes for us.
Cool. Consult the oracle.
Basically. Consult the oracle.
So you use
3463 guilty spark.
While it would be valid to ask him, I don't think he would exactly give it.
So you have to take a deep breath before you do anything because it says breath first. so just.
Yes.
No. I'll just say starting level, right? That's where you set up first.
What if you have it find all of the paths and then pick which one's shortest?
Find all the paths and pick which one's the shortest.
Yeah.
Why? Well, no, because in breadth first, you just spread out trying each path, and then once you find one, you know that's the shortest or a shortest. No?
Not sure how we'll know that it's storage.
All right, well, first off, you have to use a queue.
Okay.
To visit. Of the nodes, to visit.
Okay.
Notice last time we had a vector of keeping track of what has been visited, but now we're going to have what we need to visit.
Okay.
All right, so this can keep track of what we want to visit.
All right.
All right. So to visit dot, is it pushback? Let's find out. Or it's a queue, right?
Yeah, cute.
Should be push. Is it pushback or just push and pop?
Um,
Go internets, go, go, go.
I said push.
Should be just push, right?
Wait,
We got push and pop. All right, cool.
yeah.
Yeah. So we'll push the start.
Okay.
While to visit dot empty. So while it's actually not empty. Int current vector or current position equals to visit dot front, and then we'll do some computations. And then at the end you have to visit dot pop, and that way, at least at some point, to visit's always popping. And then the basic idea is that if nothing was found, return false. And hopefully inside of here, do some computations. We'll try and figure out what we if we can get to. All right. So we're at the start position.
Yes.
Obviously, if current position equals the end, then we're done, right?
Yes.
All right, so return true. Okay.
So this sounds like it's going to be a recursive thing as well.
No. Because we're keeping track of two visits. So we're going to go through, actually, and we're going to, let me copy this lovely for loop up here. Yeah, of our current position, right? Got a nice iterator going from beginning to end, because this is totally intuitive. So, oops. Let's go through the row. Let's go through the possible vertices we can visit. So we want to find out what we can visit. So if we can visit, namely if, what do we got? First off, mgraph am sub current position. Oh, actually we're using it. So if star it equals 1, and we need to know if we're where we are, so we need to also have that beautiful next position. Let me go ahead and put that as part of the for loop. That way it'll just be one giant for loop, because that's not problematic, is it? Let's see if it compiles. I don't think so.
Yes.
Actually, we need to have next pose up here. That's what I forgot. There we go. And then Q was not part of, that's right, so let's include Q. There we go. Perfect. All right. Probably should, does path exist? Well, let's comment this out. And we'll do return breadth first search. Start to end. Alright, didn't find anything, but it should. So, if we can visit. So how do we know if we can visit? Well, if our next position, basically the one we're operating on, does not equal current position, and star it equals 1, then we should add that to our queue. So it's going to go along the row and add every node that you can possibly visit from the point into the queue to visit. And then afterwards it's going to pop it. So it's really going, all right, I'm not here. Who can I visit? All right, let's put that in the queue. All right, let's go to the first thing we can visit in there. All right. Actually, I think right here we're going to be done. Yay, 1. It found something. This is actually not correct, because this can go into an infinite loop. because we need to also keep track of where we have been. Does that sound familiar?
Oh, yes. We need to have a,
Yeah.
has visited. Okay.
Yep. So has visited
Has visited.
the hash visited function. Yeah. So current position equals true because we are visiting. So now it's really and we not has visited. Or we should say have visited would be more correct, but that's all right.
We not has visited.
Let's see if that actually still gives the same answer. Good. So now we're getting rid of that accidentally looping through, if it ever happens. So how does we get this to print out where we're going?
Same way, I would think.
Magic.
Wait, what was the question again?
How do we get this guy? Yeah, it is magic. How do we get this guy to print out where we're going? Or what the path was?
Every time it checks the next pause, you would have it print.
Okay. Every time, well, I mean, obviously,
Or,
when we're here, we're done, right?
yeah.
Okay. But what are we printing?
I guess its current position is what you want to print.
Well, current position's the end.
Oh, you get from there. Okay. What position it is, I guess.
Yeah. Actually, I'm trying to think about how you do this in prep first. I don't know if you can.
You asking
What is the word for it that it, you know, produces the worst possible path.
Let me think about this. How do we do this? To visit. We're gonna have to use a data structure, that's for sure. I know, guys. It's gonna be crazy. But, well, the problem is when we were doing it recursively, it kept the stack always kept track of where we're going, right? Hmm.
So do we need to add further keep track? Guess not.
Well, one way you can do it is the queue, instead of just having the node, it would contain a class of not only the node, but all the paths we've taken so far.
That will work.
And unfortunately, I'm trying to think if there's a better way than that. Because your path, because you're going breadth first. Nope. No. The other way to do it, the only other way I can think of doing it is, ooh, that's going to be nasty. All right, let's do it. You have a vector of vectors, and each one will say what the path is what is it, to that location. Well, we're not going to do this because now we're getting into Dijkstra's algorithm. So that just found the position, and we're going to be happy with that. That's all we're going to do.
Okay, so we're not gonna prove that that's
The shortest, I'm trying to think if there's a way to prove this is the shortest. Easily. I just don't want to do it that way. Because we can, well, I guess we could do the path. All right, we'll do it the pathway. Class, I don't know, path. Public int m node vector of int path. And then the to visit will always be of a path. And so we'll have a path. What are we doing here? Path P, P dot M node equals start P dot, and then the vector is going to be empty, which is perfectly fine. Let's see if it's happy with that. No, not at all. Well, because we're going to have to do a lot of other things.
Yeah.
Then we need to semicolon after class definition. That's right, because it's C++. All right. And you're no longer getting back the current position. You're getting back the path P equals, I should just say, P equals to visit dot front, and then the current position would be P dot M node. And then when you want to push something, you're going to have to get a path. Ooh. Next P. Next, let's call it NP. NP dot M. What we got? Node equals next position. And then NP dot M path dot push back next position. And then you'll push that bad guy back. I just remembered we'll have to do that with this guy first. And path dot push back. Ooh. Oh, that ran. Wow. All right, so when we're done, what that actually means is now we just need a, I'm going to use I. P dot M path dot size I plus plus, and we'll do C out, and we'll have P dot M path sub I and then we'll end that with not a count, but an end line as well. Wait, what did I miss? Line to 125.
Wait, you got a semicolon.
Let's see. 9. Not quite what I was looking for.
Well, I think you only have to define your base, your current.
The problem is in path we need to push everything from our current position onto it. And is there an easy way to do that? Because once we create the vector, we need to update. We need to make sure its path is full. Oh wait, we can just set it equal to each other. That's right. So np.m path equals our current path, which is p.m path, and then we'll push back the next position. There we go. 0, 1, 6, 11, 9. So do you really think this one's easier? No. No, that's not. The recursive one is far easier than this giant mess.
Looking at it in the book and then like watching you do it, it was still. You know what? He's not gonna do it.
Yeah. Oh, the watching.
That lets me know I don't want to do that.
Yeah, you. There are many times when you need to do a breadth first search, but
Not fun.
depth first is just so much easier. All right. Now we need to take this to the next level.